Have you ever looked in a mirror and wondered, where did I get these eyes? Or why am I this tall? Well, it might feel like you just won some kind of cosmic lottery, but it's not random at all. The inheritance of every single trait is actually governed by the laws of probability. And in this explainer, we're going to break down exactly how you can calculate those odds. So let's get right to it. What really are the mathematical odds of inheriting something specific? This isn't about guesswork. There is a precise way to figure this out, and by the end of our time here, you'll know exactly how to do it yourself. Here's the game plan. First, we'll talk about why genetics is all about chance. Then, we'll get into the one fundamental formula you need to know. After that, we'll learn two super powerful rules. I call them the or and rules. And finally, we'll put it all together to solve a classic genetics problem. Let's dive in. Okay, first things first. At its core, genetics is all about variation. You know, the differences we see all around us between any two living things. But it turns out, this variation comes in two main flavors. So on one side, you have what's called discontinuous variation. These are the either-or traits. A perfect example is blood type. You're either A, B, AB, or O. There's no in-between. They're distinct categories you can literally count. Then on the other side, there's continuous variation. This is for traits that exist on a spectrum, like your height or your weight. These usually end up looking like a bell curve when you plot them out. For what we're doing today, we're going to stick to the clean, countable world of discontinuous variation. All right, let's get to our main tool, the math. And hey, don't worry, it's way more straightforward than you might think. We're going to use one single core formula to unlock all our genetic predictions. And here it is. The probability of anything happening is just the number of ways that one specific thing can happen, divided by the total number of all the things that could happen. It's really just a fraction, a ratio that tells you how likely your outcome is. The key is you have to know all the possibilities to figure out the odds of just one of them. And that final number, that probability, is always going to be somewhere between 0 and 1. If you get 0, it's impossible. It's never going to happen. If you get 1, it's a sure thing. Absolutely certain. Everything else just falls somewhere in that range. Let's make this real with a quick example. What's the chance an offspring gets an X chromosome from the father? Okay, step 1, what are the total possible outcomes? Well, sperm can carry either an X or a Y chromosome, so that's 2 total outcomes. Step 2, what's our favorable outcome? We're looking for the X chromosome, so that's 1. Now we just plug it into our formula. 1 divided by 2, the probability is 1/2, 50%. See? Simple as that. So we can figure out the odds of a single event. But what if we're interested in a couple of different outcomes? You know, what are the odds that one thing or another thing happens? That's where we need our first big tool, the addition rule. This rule is for what we call mutually exclusive events. That's just a fancy way of saying if one of them happens, the other one can't. A pea plant can't be both super tall and a dwarf at the exact same time, right? So when you want to find the probability of one outcome or another, you just add up their individual chances. Here's the cheat code. OR means add. Let's try it out. Imagine we cross two heterozygous tall plants. All that means is each parent has one dominant tall gene, we'll call it big T, and one recessive dwarf gene, little t. So the question is, what are the odds their kid is either homozygous tall, which is big T, or dwarf, which is little t, little t? And this table here lays it out perfectly. If you map out all the possibilities, you'll see the chance of an offspring getting 2 big T genes is 1 in 4. The chance of getting 2 little t genes is also 1 in 4. And since we're asking for one or the other, we just use our addition rule. 1/4 plus 1/4 equals 2/4. That simplifies to 1/2, or a 50% chance. Okay, so that's the OR rule. But what if we want to know the probability of two different things happening together? Not one or the other, but one and the other. For that, we need our second big tool, the multiplication rule. This rule is for what we call independent events, where the outcome of one has absolutely no effect on the outcome of the other. For instance, a plant's height is totally independent of its seed texture. So, to find the probability of both of those things happening, you multiply their individual probabilities. And here's the other cheat code. And means multiply. So, to set us up for the grand finale, let's just lay out the individual probabilities we'll need. From that heterozygous cross for height, the odds of a plant looking tall is 3/4, and the odds of it being a dwarf is 1/4. And for a similar cross with seed texture, the odds of smooth seeds is 3/4 and wrinkled is 1/4. These are our building blocks. All right, this is the moment we've been building up to. We are now going to combine both of our rules, the and the or, and all our individual probabilities to solve what's called a dihybrid cross. That's a genetic problem that looks at two different traits at the same time. And this table just illustrates it so well. Check it out. To find the probability of an offspring being tall and smooth, we multiply their individual chances. 3/4 times 3/4 gives us 9/16. What about tall and wrinkle? Well, that's 3/4 times 1/4, which is 3/16. And we do the exact same thing for dwarf and smooth, and finally for dwarf and wrinkle. Each one is just a simple multiplication. Now, let's just focus on that last number for a second, 1/16. That is the probability of getting the absolute rarest combination, an offspring that is both a dwarf and has wrinkled seeds. And think about this. We figured that out without having to draw some massive 16-square Punnett chart. We just used a simple multiplication rule. That's the real power of probability. Now, this principle we've been using, it has a formal name, the law of independent events. And our source material sums it up perfectly right here. The probability of the simultaneous occurrence of two independent events is a product of their individual probabilities. That one sentence is the engine driving all of these genetic calculations. So, there you have it. We've learned how to calculate the odds of what might happen. We can kind of predict the future, in a genetic sense. But this brings up a really fascinating question, doesn't it? What about the past? How do we map and understand traits that have already been passed down through generations in a family? Well, that's a whole other story, one that gets into things like human pedigrees, but it's definitely something to think about.